Hi, welcome back to the Network Plus Certification video series. I'm Mike Redmond, Master Trainer, here to help guide you through your successful journey of becoming a Network Plus certified technician. We're going to walk through a wide variety of topics, starting with basic network concepts all the way through network management and security. In this segment, we're going to talk about TCP/IP basics. I'll describe the TCP/IP protocol suite and how it works, explain CIDR and subnetting, and describe the functions of static and dynamic IP addresses. First, let's start with a little bit of history. You'll remember from previous modules our discussion of the OSI layers, Chapter 3 to refresh your memory, through Chapter 6. Well, we detailed layers 1 and 2. We also looked at some of the Ethernet network technologies. Now we're going to explore the software side of networking. Certain rules, if you will. Individual rules are called a protocol. The protocol suite is a set of rules, beginning with IP. That's the IP of TCP/IP. Most of TCP/IP takes place in the internet layer and higher. The link layer is not strictly part of the TCP/IP protocol. It actually encompasses the physical signaling and the media and devices that you're using. TCP/IP takes place at various layers of the TCP/IP model. Like I said, the link and network interface layer are not included. Most of it happens at the network and transport layers. TCP/IP consists of different layers of data. Each layer has a different PDU, and remember, each layer below encapsulates the layer above with additional headers and sometimes footers. The packet payload, for example, can be a TCP/IP segment, and that consists of data from the layers above and a sequence number. The internet layer protocols are concerned with logical addressing. That's your IP address. IPv4 is an older standard, whereas now we're moving to IPv6 because we've run out of IPv4 addresses. The Internet Protocol consists of a 14-field header. We're not going to go into depth into all of them, but here are a few fields of that header. It will consist of the version, the header length, differentiated service code points, and a time to live. Remember that the IP layer is an upper layer protocol. The transport layer of TCP/IP is TCP. It uses both UDP and TCP. Depending on the protocol that you're using will determine if the data is connection-oriented or connection-less. Application layer protocols determine whether they use TCP or UDP and use specific TCP and UDP ports to signify which application protocol receives the data. TCP by far is used the most of the application layer protocols. It establishes a connection using what's called a three-way handshake of SYN, SYNAC, and ACK. This ensures that the communications are synchronized between the two hosts. TCP also uses headers that can contain information such as the port number, the sequence number, any required flags, and of course the ACK number or the acknowledgements. TCP's protocol data units, or PDUs, are called segments. Next, we have UDP, the connection-less oriented protocol. It doesn't worry about synchronization or error. It's more of a fire and forget type of protocol. For instance, streaming video and music, as well as VoIP and DNS, use UDP. UDP's PDUs are called datagrams. Next, we have the application layer protocols. These, again, are upper layer protocols that interact directly with APIs and the applications to send and receive data, like HTTP, FTP, and DHCP. However, they do make use of particular lower layer protocols like TCP and or UDP using specific port numbers. Here's a look at a TCP header in a program called Wireshark. Now, let's take a little deeper look at the Internet Protocol. The TCP/IP suite supports both simple and complex networks. With TCP on LAN over Ethernet, it's a small network sending computer broadcasts using the MAC address. Broadcasting is disastrous, however, on a large network. To overcome this, we use IP addressing. There is a unique IP address per host, unique addresses per logical network. They communicate between LANs without a constant broadcast having to be sent. With IPv4, there is a 32-bit value to each IP address. Each value is broken up into 4 groups of 8. Each 8-bit value converted into a decimal number, you get 0 through 255. The Network Plus certification expects you to know and understand the conversions between binary and decimal. Here's a chart to help you out. Next, the IPv4 IP address is converted. It's displayed as 192.168.4.2. We call this the dotted decimal notation. Again, you should know how to convert the dotted decimal notation to binary and back. To do this, it really is fairly easy. A simple calculator will help you out. Simply enter the value in a decimal view, then switch to the binary view to convert the value. The leading zeros don't display on your calculator. However, the leading zeros are important when working with IP addresses. Remember, 1 is on and 0 is off. Again, every MAC address is unique in the world. However, every IP address must be unique for its own LAN. There are several different utilities that you can use for displaying the IP and MAC addresses. Every OS has at least one GUI tool. For instance, the Mac OS, you'll use the Network Utility tool. As well as every operating system has a command line utility. For Windows, it would be ipconfig. For Unix, Linux, and Mac, it would be ifconfig. So for an IP address, you must be sure to do three things. First, give each LAN its own identifier. Next, allow the routers connecting the LANs to use the network identifiers to send packets, and then give each computer a way to understand a packet that's intended for that computer on the local LAN. So to perform these three actions, here's how it works. All computers on the same LAN must have the same network ID. Each computer on the same LAN must also have a unique host ID. To accomplish interconnection, it requires a router to connect. The router requires a network connection and IP address on each LAN. The IP address of the router's connection to a LAN is called the default gateway. Network administrators often give the lowest host address, like the .1 address, to the router as its gateway. So how do the routers keep this straight? Well, they use a built-in router table. This is used by the router to determine where to send the packets. Next, step 3, remember you must give each computer a way to understand when a packet destination is local or on the internet. To do this, we use what's called the subnet mask. If the computer is sending to a host on the same network, it will broadcast for a MAC address. However, if it's sending to a host on another network, it will send that data packet to the default gateway. The way the router understands this is by the computer using the subnet mask to determine where to send that packet. So an example of a subnet mask for a Class C address would be 255.255.255.0. You can line up the IP address with a corresponding subnet mask in binary notation. You'll take the portion of the IP address that aligns with the ones on the subnet mask, and that's your network ID. The portion of the IP address that aligns with the zeros of the subnet mask, that is your host ID. So as the computer continues to identify where to send its data, the sending computer compares the destination IP address to its own IP address using the subnet mask. If the destination IP address matches the computer IP, wherever there's a 1 in the subnet mask, the computer knows that its intended destination is local. If, however, the destination IP address does not match, it then knows that it needs to use the default gateway. When its destination address is a local address, the sending computer sends out an ARP, or Address Resolution Protocol broadcast, to determine the destination computer's MAC address. That ARP packet contains the sending computer's IP address as well as its destination address. Once received, the destination computer responds to the ARP request by sending an ARP response. Once received, the sending computer can now send data to its destination. Next, when the sending computer discovers that the destination address does not have the same network ID as it does, the packet must be sent to the default gateway. The sending computer must send out an ARP for the MAC address of the default gateway. Now, understand that you will see multiple ways to indicate the subnet mask. The classic way would be with dotted decimal notation, like 255.255.255.0. However, if you ever see a slash and perhaps a 24, well, that's just a shorthand way of indicating the same subnet mask. We call that CIDR notation. So essentially an IP address followed by the slash and then a number, all it's doing is describing the IP and the address in one simple statement rather than requiring two different lines to say the same thing. It's important for network administrators to enter the correct IP address and subnet mask when configuring the NIC. The network software really can do the rest from there. I mean, if you want your computer to work and work properly on a routed network, you must configure the computer correctly with an IP address, the subnet mask, and the default gateway. So keeping in mind that no two devices on the internet can share the same IP address, an organization called IANA, or the Internet Assigned Number Authority, tracks and disperses IP addresses in chunks called classes. It oversees several regional internet registries, and in turn, it passes out IP addresses to the larger ISPs, like Comcast. These classes are Class A, Class B, Class C, Class D, and Class E. The Network Plus certification expects you to know and understand each of these classes as well as their address ranges. So Class A, B, and C are pretty easily understood. However, Class D and Class E's have a tendency to confuse some. So there's three ways to send a packet. You can either use broadcast, unicast, or multicast. Broadcast, you're going to send to every computer on the LAN. Unicast is a one-to-one communication, and multicast is a one-to-many communication. Originally, IP address space was fairly liberally distributed. Unallocated IP addresses became scarce, however. So the solution to this was a somewhat new method of thinking. It generated blocks of IP addresses. We call that the classless interdomain routing system, or CIDR. So let's take a look at what CIDR does for us. The entire concept of CIDR is based on subnetting. Subnetting chops up single class IP addresses into smaller groups. Understand that CIDR and subnetting are virtually the same thing. Subnetting done by an organization on a block of addresses to create multiple subnetworks. Whereas CIDR is usually done by the ISP on a block of addresses to create multiple subnets. This is what it passes out to its customers. Subnetting is a more efficient use of IP addresses. It enables separation of network addresses, which is a key security concern. It also enables the conservation of bandwidth. Subnet masks are the cornerstone of subnetting. So let's look at an example. Let's say that you're visiting your local Starbucks. You have 60 computers and you need to subnet them into 3 different subnets. Well, 40 of those computers are public computers. Say they're the customers. 10 computers belong to the back office, and 10 more computers are wireless clients. We would identify this network with a network ID. For instance, 192.168.4/24. So to give each computer a unique host ID, we begin with the given subnet mask and move it to the right until you have a number of subnets that you need. At this point, you really don't need the dots, so you're not going to be limited by /8, /16, or /24. When you create subnets, you can create subnets using /25 or 26 or even /22. So by creating these subnets, you change a 0 to a 1 at the end of the subnet mask. So your first subnet changes from /24 and now becomes /25. Next, you need to be able to calculate how many hosts can live on any given subnet. So if you were permitted the entire subnet range of 192.168.4.1 all the way through 192.168.4.254, you would have 254 available hosts. The way to calculate your host formula would be 2 to the n minus 2. Remembering you must reserve an IP address for the network and for the broadcast address. This is an important formula for you to memorize. So a little more quick math. If you wanted to calculate the hosts on a /16 network, you would recognize that there are 16 zeros as part of the host ID. That would give you roughly 65,534 hosts. The way this is calculated is you take 2 to the n, or 2 to the number of zeros in the subnet mask, and subtract 2, one for the network ID and another for the broadcast ID. Let's try another one. So to calculate the hosts on a /26 network, you would take the /26 network, which has 6 zeros as part of its host ID. Then take 2 to the n, or 2 to the number of zeros in the subnet mask, and subtract 2. That should give you 62. So now that we know how to identify the available host space on our subnets, let's give it a try. We know we need to convert the 192.168.4/24 network into the available subnets. So step 1, write out the existing subnet mask. It should look something like this. Next, you're going to need to draw a second line, 1 digit to the right. So understand this is just a little trick of mine. This not official terms per se, but what we've done is we've broken our subnet mask into 3 areas: the default subnet mask, the network ID extension, if you will, and then we've begun identifying hosts. This is now a /25 subnet mask. So here you see the default subnet mask, the little network extension in there, and then my available host space. Remember, a subnet mask is always 32 binary digits long, a string of ones followed by a string of zeros. When we put periods between every 8 digits, we've now converted it into dotted decimal notation. So the resulting subnet mask of what we've done is 255.255.255.128. It's important for you to follow me here. You've got to get used to the idea of subnet masks that use more than 255s and zeros. It's not unusual to see a subnet mask of 255.255.255.224 or even 255.255.128. Now, we're ready to calculate our subnets. Starting with a beginning subnet mask, you extend the subnet extension until you have the number of subnets that you need. So there are some simple rules when it comes to calculating subnets. For instance, to subnet /24 to /26, it adds 2 digits. This is creating essentially 4 new network IDs. Next, we need to convert the original network ID into binary and add the 4 different network ID extensions to the end of them. So now we have the possible network extensions, in binary at least, as 00, 01, 10, and 11. Those are our 4 new networks. When you stack them all on top of each other, they would look a little bit like this. So now we can see, with our 4 new networks, the possible address ranges within those networks. So now, with our new /26, our first network has the available host space of 192.168.4.1 through 192.168.4.62. Our second, 192.168.4.65 and 192.168.4.126, and so on. This is an important concept for you to get your head around, so let's do a little more practice. We're going to create a /27 subnet. We do this by first moving the network extension over 3 digits. Next, we need to calculate the host address ranges for each usable new subnet. So starting with 192.168.4.0/24, that's our first subnet, you'll see that it gives you the possible address range of 192.168.4.1 through 192.168.4.30. You'll continue calculating out in this fashion until you get to the last possible subnet of 192.168.4.225 through 192.168.4.254. This is all done by just simply moving the network ID extension, the required digits, to the right. So how do we come up with these numbers? Well, the manual binary to dotted decimal conversion of this It would look like this. You would write bit values in decimal from left to right. First, you take the binary value of one dotted octet portion and place ones and zeros under the appropriate positions. So 1, 0, 0, 1, 0, 1, 1, 0. The conversion would be 128, 64, 32, 16, 8, 4, 2, and 1. So now, wherever you see a 1, you need to add that digit together. So we see a 1 under 128, 16, 4, and 2. When we add those together, 128 plus 16 plus 4 plus 2, that equals 150. Next, we need to place the decimal value above the first value on the left, which extends, and then subtract and place a 1 to represent this binary value, or on. Then place the remainder above the next bit value. So that is the classic way to do it. Now let's take a look at CIDR, or subnetting, in the real world. We'll walk through two situations. One situation in which subnetting takes place, like with your ISPs, they receive a class license from IANA and then subnet those class licenses for each of its customers. Now, we're going to assume that these are fairly large customers. Your ISP will then take those subnets, and once distributed, they will make their own subnets. So why is it important to learn subnetting? Well, aside from the CompTIA Network Plus exam requiring it, there's a good chance that you'll contact an ISP and get a CIDR address. In addition, some of the more advanced IT certifications like Cisco and Microsoft also require this knowledge. Next, let's take a look at how to use these IP addresses. So we've walked through how to assign IP addresses to computers, and we've talked a little bit about some specialty IP addresses, but let's discuss a little more in depth. There are a couple of different ways to assign an IP address to a computer. You can do it through static addressing, that's by manually typing the IP address in each computer, or you can do it by dynamic addressing. This is when the server would automatically pass out IP addresses to corresponding requesting computers. So if you were going to use static IP addressing, you will need to type in its address, its subnet mask, and its default gateway. For instance, assuming that you have a Class C license for 192.156.4/24, you can do whatever you want with it on your own network. Remembering that every IP address must be unique, you don't have to use the numbers in any particular order, they just must be unique. So we'll walk through some general best practices. Generally, you're going to give the default gateway to the first host IP address in the network ID, because we want to try to use our IP addresses in a logical and some kind of sequential order. You also should want a way to discern whether you're dealing with a client or a server. So you should probably try to separate servers and clients' IP addresses. However you decide to do it, write down what you're doing so the person who comes behind you can understand your network architecture. So to give each computer its IP address, its subnet mask, and its default gateway, it's a little different in different types of operating systems. For instance, in Windows, you'll use the IPv4 properties dialog box, whereas for Mac, you'll run the network utility in the system preferences. Next, after adding the IP information to at least two systems on the network, you're going to want to verify their connectivity. We do this using the ping command. A successful ping confirms that those two systems can communicate. However, if the ping is not successful, you're going to need to go in and check the IP settings, or you possibly might need to check the connections or the drivers. As you can tell, this is a fairly labor-intensive process. Generally, you're only going to use static IP addressing for critical systems. Most systems today are going to use dynamic IP addressing. With dynamic IP addressing, generally you're going to use the DHCP protocol, or Dynamic Host Configuration Protocol. By far the most popular form of dynamic IP addressing. However, there is an older version that we called BootP. Dynamic IP addressing automatically assigns an IP address whenever a computer connects to a network. I mean, really at its heart, DHCP uses a pretty simple process. First, the computer is configured to use DHCP, and then, depending on the operating system, this happens to be a Windows machine, it will then hand out the next available IP address. For instance, your DHCP server is usually configured to pass out IP addresses based on scope, subnet mask scope, default gateway scope, and then we'll give out other information that we'll talk about later. So how does all this work? Well, when a DHCP client, your computer, boots up, it requests or broadcasts a DHCP discovery packet. Basically, that discovery packet just says, hey, are there any DHCP servers out there? I need an address. Your DHCP server then responds with a DHCP offer, and that DHCP client then responds with a DHCP request. Now that they've mutually agreed, the DHCP client will then accept whatever IP address it's given with what's called a DHCP lease. Now, the DHCP lease is set for an amount of time, usually between 5 and 7 days. At the end of the lease time, the DHCP client, your computer, makes another DHCP discovery message, and then the process starts over again. Some of the problems that you can run into with DHCP is when a DHCP client tries to get a DHCP address and fails. You can generally tell this because the operating system, most of them, are going to give you an error message, or the DHCP client will have an IP address that starts with 169.254. That 169.254 address is what is called the Automatic Private IP Addressing, or APAPA. It's a self-assigned IP address. It allows computers on the same LAN to communicate. However, a client with an APAPA address does not have a default gateway, so clients using APAPA cannot access the internet. This is a telltale sign of a DHCP problem. Once recognized, a DHCP problem usually is pretty easy to diagnose and fix. For instance, in Windows, just open the command line and type ipconfig \renew. Sometimes you'll need to force the computer to release its existing IP address to obtain a new one. You'll do this by, again, opening the command line and typing ipconfig \release and then ipconfig \renew. You can do this with Linux by typing ifconfig and then the interface address. In this case, we're going to deal with Ethernet 0 and administratively shut it down. And then we'll tell it to come back up simply by typing in the same command again, ifconfig, and then the interface address, and then the word up. Now, there are some special IP addresses other than the APAPA address, and this would be the loopback address. Your loopback address is 127.0.0.1. Sometimes you might hear this referred to as home. So other than the APAPA address and the home address, we've talked about the private address space, the Class A, Class B, Class C, which has a range of, for Class A private space, will be 10.0.0.0 through 10.255.255.255, all the way through a Class C, which is 192.168.0.0 through 192.168.255.255. All other addresses are considered a public address. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time.